Hi, today we're diving into sorting algorithms. Introduction to sorting algorithms. Sorting algorithms are methods to arrange data in a specific order, like numbers from smallest to largest. We'll cover three beginner-friendly ones: bubble sort, selection sort, and insertion sort. Sounds exciting. Sorting is like organizing your books on a shelf by height or alphabetically. It puts data in order, say, ascending, small to large, or descending, large to small. This makes it easier to search, analyze, or display data, like sorting a contact list by name. Think of it as tidying up a messy deck of cards. Makes sense? Yup, totally. So what's the first algorithm? Bubble sort. Let's start with bubble sort, one of the simplest sorting algorithms. Imagine a row of numbers, like cards in random order. Bubble sort repeatedly compares adjacent numbers and swaps them if they're in the wrong order. It's called bubble sort because larger numbers bubble up to the end of the list with each pass, like bubbles rising in water. Pretty cool, right? Haha, love the bubble analogy. So, we just keep swapping until it's sorted? Exactly. Let's break down how it works. Approach. Here's the step-by-step process for bubble sort. Start at the beginning of the list. Compare the first two numbers. If the first is larger than the second, for ascending order, swap them. Move to the next pair, second and third numbers, and do the same. Continue until the end of the list. After this, pass. The largest number is at the end. Repeat for the remaining numbers, stopping one position earlier each time, since the largest numbers are already in place. Stop when no more swaps are needed. The list is sorted. It's like pushing the biggest number to the right each round. Want to see it in action? Definitely. Can we try it with dry run? Awesome. Let's use the array. Let's sort it in ascending order with a dry run. Initial array, 5, 2, 8, 1, 9. Pass 1. Compare 5 and 2. 5 greater than 2. Swap. 2, 5, 8, 1, 9. Compare 5 and 8. 5 less than 8. No swap. 2, 5, 8, 1, 9. Compare 8 and 1. 8 greater than 1. Swap. 2, 5, 1, 8, 9. Compare 8 and 9. 8 less than 9. No swap. 2, 5, 1, 8, 9. After pass 1, 9 is in place. Pass 2. Compare 2 and 5. 2 less than 5. No swap. 2, 5, 1, 8, 9. Compare 5 and 1. 5 greater than 1. Swap. 2, 1, 5, 8, 9. Compare 5 and 8. 5 less than 8. No swap. 2, 1, 5, 8, 9. Stop before 9. Now 8 is in place. Pass 3. Compare 2 and 1. 2 greater than 1. Swap. 1, 2, 5, 8, 9. Compare 2 and 5. 2 less than 5. No swap. 1, 2, 5, 8, 9. Stop before 8. Now 5 is in place. Pass 4. Compare 1 and 2. 1 less than 2. No swap. 1, 2, 5, 8, 9. Stop before 5. No swaps, so we're done. See how the largest numbers bubble to the right? That's so clear. Imagine the array as boxes, with numbers sliding around. Initial, 5, 2, 8, 1, 9. Pass 1. 5 swapped with 2. 8 swapped with 1. Pass 2. 5 swapped with 1. Pass 3. 2 swapped with 1. Pass 4. No swaps. Picture the biggest numbers settling right, like heavy balls. In an app, you'd see bars moving, but this shows the flow. Clear? Yeah, I see the bubbling now. What's the code like? Let's see the pseudocode. Let's write pseudocode, a general way to describe the algorithm. Function bubble sort, array, n. For I from 0 to n minus 1. Set swapped equals false. For j from 0 to n minus I minus 2. If array j greater than array j plus 1. Swap array j plus 1. Set swapped equals true. End if. End for. If swapped equals false. Break. End if. End for. Return array. End function. This loops through the array, swaps adjacent elements if needed, and stops early if sorted. The swap flag optimizes it. Makes sense? Yup, got it. How fast is it? Time and space complexity. Let's check efficiency. Time complexity. Worst case, reverse sorted. For example, 9, 8, 5, 2, 1 needs n-1 passes, each with up to n-1 comparisons/swaps. So big O of n squared. For 100 numbers, approximately 10,000 operations. Best case, already sorted. For example, 1, 2, 5, 8, 9, 1 pass, no swaps. So big O of n with the swap flag. Average case, big O of n squared, as multiple passes are typical. Why slow? Lots of comparisons and swaps for large arrays. Space complexity. In place, using only a few variables, for example, swapped. So, big O of 1 extra space. Bubble sort simple, but slow for big lists. Ready for selection sort? Let's do it. Selection sort. Selection sort is another easy algorithm. Imagine picking the smallest number from a pile and placing it at the start, then repeating for the rest. It selects the smallest element in each pass and puts it in its final position. It's like sorting cards by finding the lowest card each time. Oh, so we're hunting for the smallest each time? Yup, exactly. Let's see how it works. Approach. Here's the process. Start with the first position. Scan the entire unsorted portion to find the smallest number. Swap it with the number in the first unsorted position. Move to the next position and repeat, ignoring the sorted portion. Continue until all positions are filled. It's like building the sorted array from left to right. Want to try it? Sure, same numbers. Dry run. Let's use 5, 2, 8, 1, 9 again. Initial array, 5, 2, 8, 1, 9. Pass 1. Find smallest in 5, 2, 8, 1, 9, 1 at index 3. Swap 1 with 5, first position, 1, 2, 8, 5, 9. 1 is now in place. Pass 2. Find smallest in 2, 8, 5, 9, 2 at index 1. No swap needed. 2 is already there. 1, 2, 8, 5, 9. 2 is in place. Pass 3. Find smallest in 8, 5, 9, 5 at index 3. Swap 5 with 8, 1, 2, 5, 8, 9. 5 is in place. Pass 4. Find smallest in 8, 9, 8 at index 3. No swap needed. 1, 2, 5, 8, 9. 8 is in place. 9 is already last, so done. Notice how we're locking in one position per pass? That's cool. It's like picking winners one by one. Visualization. Initial, 5, 2, 8, 1, 9. Pass 1. 5 swapped with 1. Pass 2. No swap. Pass 3. 8 swapped with 5. Pass 4. No swap. Imagine filling slots from left to right with the smallest numbers. Clear? Yup, I see it. What's the pseudocode? Let's see the pseudocode. Here's selection sort pseudocode. Function selection sort, array, n. For I from 0 to n-2. Set min_index equals I. For j from I plus 1 to n-1. If array j less than array min_index. Set min_index equals j. And if for min_index not equal to I. Swap array I, array min_index. And for return array. End function. It finds the smallest in the unsorted part and swaps it into place. Simple, right? Yeah, it's straightforward. How's its speed? Time and space complexity. Let's analyze. Time complexity. Worst case, any order each pass scans n-I elements, so total comparisons. Thus, big O of n squared. Best case, same, big O of n squared, because we always scan the full unsorted part, even if sorted. Average case, big O of n squared, similar to worst case. Why? Always does the same number of comparisons, unlike bubble sort's early exit. Space complexity, in place, using only a few variables. So, big O of 1 extra space. Selection sort's also slow for large lists, but makes fewer swaps than bubble sort. Ready for insertion sort? Let's keep going. Insertion sort. Insertion sort is like sorting a hand of cards. You take one number at a time and insert it into its correct position in the sorted portion of the array. It builds the sorted list gradually, shifting numbers as needed. It's intuitive, like arranging cards in your hand. Oh, like sliding cards into the right spot? Exactly. Let's break it down. Approach. Here's how it works. Start with the second element. Assume the first is a sorted list of 1. Compare it with the previous elements and shift larger ones right to make space. Insert the element in the correct spot. Move to the next element and repeat, growing the sorted portion. Continue until all elements are processed. It's like keeping the left side sorted and slotting each new number in. Want to see it? Yes, same array. Dry run. Using 5, 2, 8, 1, 9. Initial array, 5, 2, 8, 1, 9. Pass 1, insert 2. Sorted part, 5. Insert 2. 2 less than 5, shift 5 right. Place 2, 2, 5, 8, 1, 9. Pass 2, insert 8. Sorted part, 2, 5. Insert 8. 8 greater than 5, no shift needed. 2, 5, 8, 1, 9. Pass 3, insert 1. Sorted part, 2, 5, 8. Insert 1. 1 less than 8, shift 8. 1 less than 5, shift 5. 1 less than 2, shift 2. Place 1, 1, 2, 5, 8, 9. Pass 4, insert 9. Sorted part, 1, 2, 5, 8. Insert 9. 9 greater than 8, no shift needed. 1, 2, 5, 8, 9. The array's sorted. See how the sorted part grows? That's awesome. It feels like sorting cards. Initial, 5, 2, 8, 1, 9. Pass 1. Insert 2. Insert 8, shift 1. Pass 3. Insert 1, shift 5. Shift 2. Pass 4. Insert 9, no shift. Imagine the left side as a sorted hand, and you're sliding each new number in. See the pseudocode. Here's insertion sort pseudocode. Function insertion sort, array, n. For I from 1 to n minus 1. Set key equals array I. Set j equals I minus 1. While j greater than or equal to 0, and array j greater than key. Set array j plus 1 equals array j. Decrement j. End while. Set array j plus 1 equals key. End for. Return array. End function. It takes each element, key, and shifts larger ones to fit it in. Intuitive, right? Yeah, it's like organizing as you go. How's its performance? Time and space complexity. Let's check. Time complexity. Worst case, reverse sorted. For example, 9, 8, 5, 2, 1. Each element shifts all previous ones. Thus, big O of n squared. Best case, already sorted. For example, 1, 2, 5, 8, 9. No shifts, just comparisons. So big O of n. Average case, big O of n squared, as shifts are common. Why? Shifts can be costly for large sorted portions. Space complexity. In place, using only a few variables. So, big O of 1 extra space. Thanks for learning with me today.